Welcome to this overview of linear regression. We're going to do simple linear regression. We're going to do multiple linear regression. We're going to talk about diagnostics to check the assumptions of your regression analysis. We're going to cover just about everything that you can imagine, and we're going to do the whole thing in about 10 minutes. So buckle up, hang in there. We're going to get through this very fast. Just to let you know, at the end of the video, there will be a card on the screen that you can click on that'll let you download some cheat sheets and some notes that I've got that cover all of this in a lot more detail. You can go through this carefully in your own time. Okay, on the screen, what we've got is we've got a simple linear regression model. On the left-hand side, what I've got is the outputs that come from R. It doesn't matter what platform. You could use any other software. The outputs would be the same. They just might be in a different format, but I'll walk you through them. So easy peasy, lemon squeezy. What is a linear model? This is a simple linear model that's talking about the relationship between an exposure variable on the x-axis and an outcome variable on the y-axis. And it's saying we think that there's a linear relationship between this. So as one goes up, the other goes up, and it does that in a consistent way as you go further and further. It doesn't get, it doesn't have an exponential curve in it or anything like that. And the usefulness of these models is twofold. Firstly, you can use your model, which is the blue line, the best fit line that goes in there. You can use the model to predict, in this case, okay, let me just say this is weight of woman explained by height. Okay, height is the explanatory variable on the x-axis. Weight is the outcome variable on the y-axis. You can use the model to predict the weight of a woman given a particular height. So to predict the outcome, the value of an outcome variable given a particular value of the explanatory variable or independent variable, even outside of the range that you've got on the screen. So you could have some hypothetical height and say, what do we think the weight would be? Fine. So you can predict. The other thing is that there's explanatory power. In other words, we can say this model, you can explain how much of the change in weight can be explained by the change in height. Right. And that is linear regression in a nutshell. Let's look at the results that we've got on the left-hand side of the screen at the moment. So at the top, we've got just the model itself, right? The formula is weight explained by height and data equals woman. Easy peasy, lemon squeezy. The residuals, we're going to come back to that, but the residuals are the distance between the observed values and the model. It's kind of like the error. We're going to come back to residuals. We're going to talk about them in detail in just a few minutes. So hang on. We're going to come back to residuals. The coefficients. Any line that you draw on a Cartesian plane like this has got an intercept and a slope. The intercept is very often meaningless. Okay, and what do I mean by that? The intercept is what is the value of weight when the height when the height is naught, right? Because that's when the line will intercept. Well, there's no such thing as a woman with a zero height. So what is the weight of a woman with zero height? It's a meaningless question, and so we very often, not always, but we very often ignore the y-intercept. It's often a meaningless number in the context of the question that we're really trying to answer. The height coefficient is the slope, right? And that's 3.45. And that means that for every increment in height, and I think it's inches, so for every inch in height, in this particular data set, the weight will increase by 3.45 pounds, because this is data, not metric. Fine. In this case, if you look on the right-hand side, the p-values for both of our coefficients is significant. So it's less than 0.05. In fact, it's very, very small, so very significant. Happy days. So we're happy with that part of the model. Go down to the bottom. The F statistic, I'll just quickly cover that, tells us that at least one, and in this case we only have one, explanatory variable has explanatory power for the outcome variable. P-value very, very small. Very happy with that. Now, the two values just above that, let's look at those quickly. The multiple R squared tells us what percentage of the change in the outcome variable can be explained by the change in the explanatory variable. So 0.99 means 99% of the change in weight can be explained by a change in height. Right, that's interesting. Now, if it's a simple model, we use the multiple R squared value. If it's multiple regression, so we add in additional explanatory variables, which we're going to do in a second, we ignore that left-hand side R squared and we move to the adjusted R squared, and we would look at that. All right, so to decide between which R squared we use, we simply decide, is it a simple model or is it multiple regression, and you choose a R squared, and that's the one that you'll use. Okay, let's keep going. Let's add in another variable, and in this case we're adding in a numeric variable as part of our explanatory variables, and we're looking at tree volume, like the amount of wood in a tree, and it can be explained by a combination in this particular model of girth and height. The thickness of the tree and the height of the tree, they're explaining volume, right? And you can see we've got a model there. Height is the color of blue, and girth is the x-axis. You can represent height in different ways. You could put in a z-axis and have a three-dimensional curve if you want. It doesn't really matter, so long as you understand that both of these variables, before we actually do the model, we think may have a relationship with the volume of the tree. Okay, let's look at the model that comes out of this. Our formula at the top, we've got volume is explained by girth plus height. The plus there is important if you're working in R, and other other software may use a different way of explaining this, but we're just adding height in as an explanatory variable. We're not suggesting at this stage that there's any interaction between girth and height, and we're going to come to interactions in just a minute. Right, so we're keeping things simple just for the sake of the lesson. So girth plus height dot equals trees. Happy days. The residuals, we're coming back to talk about residuals in a minute. The intercept, the y-intercept, again, meaningless, because what is the volume of a tree with zero girth? Doesn't make sense. We're going to forget about that for now, but there are models where that's important. Right, here are our two coefficients for girth and height. Firstly, let's check that they're both statistically significant. They are. Double thumbs up. Keep going. Girth coefficient of 4.7 means for every increment in girth, the volume goes up by 4.7. Happy days. Height, for every increase in height, the volume goes up by 0.3. Both are statistically significant. Happy days. Let's look at the bottom of the results at the bottom. The F statistic, the p-value is very small, so our model as a whole works. No problems there. This is now multiple regression, not simple regression, so we use the adjusted R squared, which is 0.94, which means 94% of the change in volume of the trees can be explained by girth and height, or the combination of those two explanatory variables. Okay, happy days. Now let's add in, instead of adding in a numeric variable, let's add in a categorical variable. Right, here we've got information about fuel efficiency of cars, and the fuel efficiency decreases where engine size increases. Right, so that's, I haven't put the simple model in here just because it's not necessary. You can imagine as the engine size increases here, going from left to right, highway fuel efficiency seems to decrease, but we've disaggregated this data in the graph by drive, four-wheel drives and two-wheel drives. Okay, so let's try and understand what's going on here. The one thing I want you to notice, and this becomes important as we look at other plots that we're going to look at in just a second, is these two lines are parallel. So we don't think, so the slope of the decrease in fuel efficiency with engine size amongst four-wheel drives is the same as the slope or the decrease in fuel efficiency with engine size in two-wheel drives. So engine size, so drives, what drive it is, doesn't seem to affect the extent to which engine size impacts on highway fuel efficiency. There's no interaction. There's no dependency there. That's going to be interesting when we look at examples where there is an interaction. But I want you to take note of an example where there's no interaction, because it'll be easier to understand interactions when we look at them. Okay, so let's look at what's going on here. And by the way, I'm going to talk to you about what these results would look like if we did check to see if there was an interaction, and I'm going to address that in just a second. So we've added in drive. Displacement, by the way, at the top formula there is engine size. Drive is our two-wheel drive, four-wheel drive. Y-intercept, we're going to ignore displacement, which is engine size. As engine size increases, highway fuel efficiency decreases by 2.8. Happy days. Now, this is where people get a little bit confused, and pay attention, take a deep breath. This is what I want you to understand. We've got two kinds of drives. We've got two-wheel drives and four-wheel drives, but in our results, we seem to only have a result for two-wheel drives. What's happening there is the four-wheel drives is the reference, is a reference group, and we're comparing what would happen if we moved from being a four-wheel drive to being a two-wheel drive. You could do it the other way around. You could have four-wheel drives in the results, and you'd be comparing what would happen if you moved from being a two-wheel drive to being a four-wheel drive. Remember when we looked at numeric variables, we were saying, the displacement as the engine size goes up, highway fuel efficiency goes down, and that would apply to going from 2 to 3 to 3 to 4 to 4 to 5 to 5 to 6 to 6 to 7, any number of possibilities. With a categorical variable, there's only one possible change you could make, you're either changing from being a two-wheel drive to a four-wheel drive or being a four-wheel drive to a two-wheel drive. If there were more categories, you would compare each of the other categories to your reference group. So drive 2 over there means, and it's and the coefficient is 4.9. And by the way, all of the coefficients are statistically significant. Happy days. So what does the 4.9 mean? It means that on average, if all else being equal, if you moved from being a four-wheel drive, which is the red dots, to being a two-wheel drive, which is blue dots, there would be an increase in fuel efficiency of 4.9. Right. Easy peasy, lemon squeezy. Again, the F statistic p-value is low. Adjusted R squared, 0.73, so 73% of the change in highway fuel efficiency can be explained by a change in engine size and drive. Now, a couple of things. If I'd done this analysis and I'd put instead of a plus sign between displacement and drive, or engine size and drive, instead of a plus, if I put a times in there, it would be saying that we want to look for the interaction between these terms as well as their individual effects. I'm not going to do it now for the sake of time, but I'm going to tell you that if you put a times in there, it does give you an interaction term, and that interaction term is not statistically significant, which is what you'd expect because these two lines look so parallel. Right, so happy days. The other thing that I will tell you, but I won't show you now for the sake of time, is that as you add in that interaction term, the adjusted R square value doesn't change at all. In other words, by adding in the interaction, it's firstly not statistically significant, and secondly, doesn't improve the model at all. So we're happy to leave it out. And that's an important principle that I want you to kind of get your head around, because you need to build your model up. You may have a data set with many variables, and there's multiple ways in which you can decide which variables to include in your model. The one way is to start off with a simple model and add variables one at a time, and consider whether or not adding that variable improves the model. So is there more explanatory power? Is the statistical significance better by adding in additional the additional variable? And when you get to a point where adding in a next variable doesn't improve the model, you leave that out, and that's the model that you work with. You can do it the other way around as well. You can start with everything and take one away at a time. There are automatic ways of doing it, and there is an AIC a score that you can use, which basically penalizes. So it looks at all of the possible models that you could create. It penalizes models for having more variables, and because the more variables you have, the more you can end up with a problem of overfitting, and gives extra score to variables that have better fit. And then the model with the best score is the one that you should use. Okay, and there are automatic ways of getting to that answer. But so selecting the variables that go into your model also needs to take a lot of common sense, and needs to include your understanding of the subject matter and your understanding of the variables and the relationships between them. So you've got to bring a lot of yourself and your insights into the analysis at that point in the game. Right. Okay, so we've talked about adding in a categorical variable into our multiple regression. We've talked about adding a numeric variable. Let's talk about interactions. And before we look at the interaction, I'm going to look at a situation where, to understand the interaction, let's look at fuel efficiency explained by weight of cars. This is actually a different data set. Right, we've got fuel efficiency on the y-axis, and we've got weight of cars on the left, on the x-axis, and as the weight of cars go up, the fuel efficiency goes down. You would expect that. Happy days, it looks to be pretty linear. Now, what would happen, and I won't go through all the values on the screen at the moment, but weight of cars, as the weight of car goes up by one increment, fuel efficiency goes down by 5.3. Okay, fair enough. F statistic p-value is very low. Adjusted R is 74%. Happy days. Okay, now if we were to look at the same data, but disaggregate the data by transmission. So some of these cars are automatic, some of them are manual. Interesting. A couple of things just to note even before we start looking at the data. The one is that the F statistic p-value is still very low. We expect that. But I always look at it just like as a matter of, it's there. Interesting, the adjusted R squared has gone up to 81. So if we go back, this was a simple model, so we look at the multiple R squared. 75% of the change in fuel efficiency can be explained by a change in weight of the car. When we add in the additional variable, now 85%, adjusted R squared, 81% of the change in fuel efficiency can be explained by a combination of weight of car and transmission and the interaction between them. Interesting. So this looks like an improvement to our model. Remember, we were talking about building up the model and adding additional variables. Also note that all of the coefficients are statistically significant. Also, double thumbs up, happy days. Let's have a look at, and you'll notice in the formula at the top, I've got miles per gallon, which is the fuel efficiency, explained by weight times, not plus, times, and the AM represents transmission, right? And that means we're going to ask for an interaction term in our coefficients. Again, I'm not looking at the y-intercept. There's no such thing as a weight of car of 0. It doesn't make any sense, so we're going to ignore that. The coefficient for weight, minus 3.7. So all else being equal, so if you kept everything else constant, for every increase in incremental weight of the car of 1, there would be a decrease in fuel efficiency of 3.7 or 3.8, right, if you round up the 8, and that is in miles per gallon. Okay, so we understand that it's statistically significant. The AM manual, that's very similar to what we talked about when we're looking at the other example. This is if you were to change from automatic to manual. So if everything else was kept equal and the only change that you made was you moved from being an automatic car to a manual car, there would be an increase in fuel efficiency of 14.9 or 14.87 miles per gallon. Okay, so that makes perfect sense. Now there's the interaction term. And basically this weight of manual cars, manual transmission, weight, semicolon, manual. What does this interaction term mean? It means for manual cars, right, the effect of weight on fuel efficiency is minus 5.2, so it's 5.29 or 5.3 miles per gallon less for every incremental increase in weight than would be the case if it was an automatic car. Okay, I know that's quite a lot to get your head around as I say it, and if you watch my longer videos on this, I kind of spend a bit of time on that because I know it can be a lot to get your head around. But if you look at the plot and you listen to what I've just said, it makes perfect sense. Okay, so moving on. Now I want to talk a little bit about what are the assumptions that we make about our plot, and what are the diagnostics? How do we consider whether or not we're comfortable that these assumptions have been met? Right. There's 4 assumptions that are important. 1 about the relationship between the exposure and the outcome variable, and then 3 about the residuals. Okay. The assumption that we make about the relationship between the exposure and the outcome variable is that there's a linear relationship. Happy days. And how do we check that? There's 3 ways that we can check it. Firstly, we look just visually. It looks like because very often if it's not linear, it's obvious. You can sort of see there's an exponential curve or something, and it's obvious. So we think it's more or less linear. Fair enough. It's subjective, I know, but there are mathematical ways of getting to the same place, and I'm going to talk about that in a second. So does it visually look as if they are linear? The second thing we can do is we can look at the relationship between the residuals and the fitted values. Now, what are the residuals and the fitted values? The residuals are, as we said just now, the red line, so the amount of red line there, okay? And the fitted value is, the predicted, and in this case, miles per gallon for that same axis, that same value. Where if you plot the residuals versus the fitted values, what you want is for all of this to be very random. You want the same number, more or less the same number of dots above and below the line. You want them to be distributed evenly from left to right. You want it to be as random as possible. As soon as you see a pattern, there's a problem. And that problem, there can be multiple possible problems, but one of the problems that may cause that is the fact that you don't have a linear relationship between the exposure and the outcome variable. Okay, if you're not sure, let's say you look at these things, you sort of think to yourself, this is subjective. I want to do a statistical test. There's the Harvey-Collier test that you can do. Keep in mind that the null hypothesis for that particular test is that the relationship is linear. In other words, what you want to see is a high p-value, a p-value above the alpha, a p-value more than 0.05, and that will confirm that the assumption is met. Right. Now let's talk about the residuals. The residuals are these red lines, and we make 3 assumptions about those residuals. The first is that they're normally distributed. We're going to come back to that. The second is that they are homoscedastic. Homoscedastic. I always get that they are homoscedastic. Such a weird word. And we talk about homoscedasticity. Too weird for me. Okay. And that basically means that the variance of these residuals is evenly distributed across the fitted values. In other words, we're not seeing a pattern. We're not seeing a whole lot of large residuals on the one side of the graph and smalls on the other side. That is sort of evenly distributed across the board. And that's that. And then the third assumption is that they are independent of each other. And the time when a good example of when they're not independent, I'm actually going to show you a plot that'll illustrate that. Here, this is a time series analysis where we're looking at a group of people and we're looking at the same people at different points in time. Let's say I am the green dot at the bottom, and at 8 years they do some sort of measurement of my teeth or something, and then they measure me again at 10 years. That measurement at 10 years is not independent of the measurement at 8 years because I'm the same person. You know, I might have a particular diet, or I might have some sort of genetic disposition that impacts on my measurements, and so these measurements along my line are not independent of each other. And so time series analysis is a good example of when things aren't independent. Right. So those are the three assumptions for the residuals, that they are normally distributed. So by normally distributed, just also to be clear, you know, each of these red lines that you're seeing on the screen at the moment, you could imagine that there's a value. If they're normally distributed, there'll be very few very small ones, very few very big ones, and the bulk of them will be kind of somewhere in the middle. And so you get this normally distributed, this normal distribution of the residual values. And that's kind of more or less what you're seeing over there. But, of course, we have to check these things. So normally distributed, homoscedastic, so that the variance from across the fitted values is the same, and independent. How do we check these things? Well, the normal distribution of them, and these are basically what you're seeing at the moment on the screen, are examples of when there is a pattern in the residuals versus fitted values. And we'll talk about that in a second. But here we go. We've got a histogram of residuals. And you could look at that histogram and sort of say, well, is that a normal distribution? It's a bit iffy. You might want to think about the size of the buckets. I don't know. You still, you kind of think, well, it's subjective. Some people might say yes, some no. The plot on the right side is a QQ plot. Quintiles are points in a distribution that divide the data into two probabilities. So the median divides it into 50-50, quartiles divided into 25, 25, 25, 25, and you can get into smaller and smaller and smaller increments. If you get those quintiles of a normal distribution, and for each quintile you compare it to the quintiles of the distribution that you're trying to check if it's normal, and they are very similar, you will get this nice kind of diagonal line in your QQ plot, right? They'll go along that dotted line. So it's a nice way to visually check, is the distribution of the residuals normal? Is it normally distributed? Again, this is subjective, so you might want to do a statistical test to check. And the test you would do for that is the Shapiro-Wilk test. And again, the null hypothesis is that that it is normally distributed, so you want a high p-value for that result. A little bit unusual in stats, but that's what you're looking for there. In terms of homoscedasticity and in terms of independence, you want to see this graph on the right, the residuals versus fitted values, to be random. You don't want to see a pattern there at all. Any clumping suggests there's a problem. Okay, and here are examples. There's a U shape, there's a funnel shape. If you start seeing a pattern in these graphs, something is wrong. And what that something is it might be that there's not a linear relationship between the exposure and the outcome variable. It might mean that the residuals are not homoscedastic. It might mean that they're not independent. But there's something afoot, and that's when you're either kind of convinced that you can't use this data, or you might want to look more closely at the tests that you can do. So for the test for homoscedasticity is the Bruch-Pagan test. Again, p-value needs to be high, not low, because your null hypothesis is that the residuals are in fact homoscedastic. And for independence, you use the Durbin-Watson test. Now, the Durbin-Watson test will give you a Durbin-Watson statistic. If it is close to 2, it suggests that there is independence. And in an example like this, it gives a Durbin-Watson test result of about 0.89, which is far from 2, which means that in this case there wasn't independence, right? So it's a way of checking for independence. The last concept that I just want to kind of raise is, well, I think have we talked about collinearity? I'm not sure if we talked about collinearity, so if we have, I'm going to just cut this part out of the video. If we haven't, here goes. Collinearity is where you've got two or more variables that are correlated with each other and correlated with the outcome variable that you're interested in, so exposure variables. And they might be telling the same story and tripping over each other, and you might consider, in order for it to be a strong model without too many variables, in other words, overfitting, removing one of the two. Now, it doesn't mean you have to remove them. It means that you would consider it, and this is where your expert knowledge on the subject and your understanding of the variables and the relationships between them matters. You might not want to remove them for certain reasons, and a good reason is, for example, confounding. So what is a confounding variable? Confounding variable meets that same set of criteria, right? There's there's a strong correlation between the both exposure variables and the outcome variable, and a correlation between the exposure variables themselves. So you might think, oh, this is collinearity, we need to remove one of them. But let me give you an example of how confounding works, and you want to keep both variables in the case of confounding, because they control for each other. Here we go. You're selling ice creams, and you notice that ice cream sales are positively correlated with shark attacks. And you sort of think, well, do ice cream sales cause shark attacks? Well, the answer is we don't think that they do. But there's another variable, another explanatory variable, which is temperature. And you find that temperature is also positively correlated with shark attacks, because on hot days people swim more. But these two exposure variables, ice cream eating and temperature, are also positively correlated, because people eat more ice cream on hot days. So all three of these things are positively correlated. You do want to include both exposure variables in your analysis, because it allows you to control one for the other, and you can actually see whether or not there's a causative relationship, for example, between eating ice cream and there being increased heart attacks, shark attacks, which of course there wouldn't be. Okay, look, I hope that was helpful. There will be on the screen at the moment, there will be a card that you can click on. That card will take you to a resource library where you can download all of this and more, everything that I've explained and more, as free PDFs. It doesn't cost you anything. Okay, hope you're doing well. Take care. All the best. Bye.